All right, so welcome to our next lecture on stability of synchronization. So this lecture is going to be a bit different from the previous ones. So the previous three were really intended to introduce the material, whereas now in this lecture, I will assume that you have at least familiarized yourself with it. So let's say that you have at least read the material and you're up to speed and you know at least in a nutshell what's going on. So I will assume I will go a bit faster in this lecture. I will assume you have now at least seen um, what's going on for stabilizing the synchrony space in networks. So in this lecture, I will instead finally focus on hypernetwork systems. So what I'm going to do is I'm going to have a bunch of nodes as usual, and they have an index and they evolve each of them according to some not necessarily linear function. So for each node, we have a single ODE. We in fact have the same ODE. So we get something like this as before. So now I'm going to couple them together again, precisely as before. So f is here a function from the phase space of each individual node to itself. And I'm not going to assume that's necessarily 1D. It's going to be k-dimensional. This is supposed to be a k. So it goes from Rk to Rk, and it's not necessarily linear, right? And so now I'm going to couple all these guys together. So let's say that the subscript I is in a set from 1 to n. So those are the nodes. And I will couple them together to some other nodes. But there's a twist. Instead of looking at networks, I will now look at hypernetworks. And I'll tell you precisely what I mean by that. So we have a coupling just as usual. We have an adjacency matrix, so you can see that matrix A as being taking values 1 or 0, but there will now be three indices. So it's not so much a matrix as that it is a tensor, if you like. So the state of node I is going to depend on the state of the other nodes, but it will do so via triplet interaction. So here's, of course, the thing that we're interested in. It's going to be h of xj, which is the state of node j, minus 2 times the state of xi. So that I remember we're in the formula for xi dot. So this is the node itself, but plus xk. So this is, of course, slightly different than the context we had before. And I am going to assume that h, for some reason I call that a capital, is also from Rk to Rk, and it's also not necessarily linear. So I'm going to really go to the most general setup. I will assume that h of 0 is 0. And by doing that, I again get that the fully synchronous manifold, so the space where all the xi are equal to themselves, are equal to each other, is flow invariant. And this is very easy to check. You just, again, as always, plug in the equations for, right? You just plug in x1 is x2 is x3 is some fixed value s, and you note that the equations will be the same on that space for each of the nodes. And it will, in fact, of course, be xi dot is f of xi, right? Because this whole part vanishes because h of 0 is 0. So this space is going to be invariant. So we again have this synchrony space going on. And so we can again ask the exact same questions. Uh, what can I do with the coupling strength alpha over here to maybe make this synchronous space stable? And again, we cannot change the dynamics on the manifold, on the fully synchronous manifold, right? Because there we know it's just going to be xi dot is f of xi. So what are we doing here? Well, we have a bunch of nodes, right? So this is node I, and then we have node J and node K. And the state of node I depends on the state of the others, right? So of its neighbors, if you want, J and K, but not necessarily via direct connections, but instead it takes this difference of three nodes, and that difference is the way in which node I feels its neighbors. So we only have these kinds of um, these kinds of constructions. So this is why we talk about a hyper network, right? So instead of having ordinary dyadic connections, we now have, which was like xj minus xi, we now have these higher order terms, these higher order combinations via which I feels its environment. So it's useful to introduce again some matrices essentially, right? So let's see, what we will define is sort of this new Laplacian. So it will be clear why I call it a Laplacian, even though we're not talking about networks, right? But we're now talking about hypernetworks. If I plug in a big vector x and I look at the ith component, then this will be exactly this sum that we have over there of these terms. So this goes from j and k is 1 to n. Oh, j is k from 1 to n of this a I j k. And then I just plug in those triples. Well, I'm going to plug in the triples with a minus because I want the diagonal to be positive, right? So this will in fact be minus xj minus xk, and then plus 2xi, right? Because just as with networks, I want this matrix L to have nice spectral properties, namely all non-negative eigenvalues. So I'm going to essentially write what's going on here, but with a minus sign. And so what do these matrices look like? How do they look? So at spot I, right, of our matrix, we are going to have a 2 at the ith spot over here, right? And then at the jth spot and the kth spot, we will have a -1. And the rest zeros, or rather, we have a bunch of these columns, a bunch of these rows, sorry, that we're adding together. So there could, of course, be this 2 could become a 4, and it could be more -1 spread over, but it's going to be the sum of rows like this, which of course correspond precisely to these terms over here. Remember, the A, I, J, K are just going to be 1 or 0. It can also be weighted. Things don't change that much, but let's just say for convenience that this is just going to be taking values either 0 or 1. So we have these matrices, these new Laplacians L, and as usual, we see that L is going to be symmetric, right? Which is what we're going to assume. So L is going to be symmetric, and if we make that assumption, then we see that lambda 1 is going to be 0 because we will have the fully synchronous space again. And then, so this is going to be 0. And then we have all non-negative eigenvalues and so forth. Let's say n of them. Let's say we have, well, we already said that we have n nodes. Okay, so far so good. So we are in more or less the same situation as we were. And then indeed we can start playing the same game. We can start looking at a synchronous solution and we can think what happens if I make a small perturbation to that synchronous solution. So let's say that we have a new solution to our system. So this is just x, and I know the ith component. And I'm going to write that as a synchronous solution. So let's say Si, but because S is a synchronous solution, I can just write that as little s, right? Because the components, by definition of synchronous solution, all of the components are the same. So this is, of course, a vector in Rk. And I will take a small part u, ui. And so the corresponding vector u, right? So the corresponding vector, let's see how I'm going to write that. Well, let me write it as follows to make it completely clear. So we know that this eigenvalue has a corresponding eigenvector, which is just all ones. So I'll write that with the 1. Of course, this is a vector 1, right? This has n entries, and they're all 1. So suppose that the other ones, they have some entries v2 up to vn, by which I mean these are, sorry, I should say eigenvectors, right? So this is our L over here. This is our L. L has a bunch of eigenvalues and has some corresponding eigenvectors. So these are the eigenvalues, and these are the corresponding eigenvectors. So the eigenvectors, they of course live in Rn. So what I've done really here is I've written xi, or rather I've written x as something of the form 1, which corresponds to the numbering, really, the Rn corresponding to the network, tensor the internal dynamics, so tensor just a small s, and then plus the sum over others. So maybe say L is 2 to n, and then I take those other eigenvectors, and then of course tensor some 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 vectors, right? So some vectors in Rk, which will be YL. So this is my part U, and this is my part S. And I'm going to assume that U is small. So I can just say that the eigenvectors are fixed, right? They have a fixed size. I just fix them once and for all. I could maybe say that they have absolute value, that they have norm 1, but I fix these eigenvectors over here. So really all that I'm saying by saying that U is small is saying that the YLs are small, or at least they start small, right? So that's of course what we want to know. We want to know if they stay small and indeed if they go to zero. Because if they go to zero, then we have synchronization. Then this, if I let time run, then this X will start looking like this S, which means that we go to the fully synchronous manifold. So what we want is for the U's to go to zero instead of blow up, for instance. And so that is our way, that is the way that we're going to argue synchronization. All right, so like I said, we plug in these equations and we just see, right, what's going to be the behavior of U. So this is precisely the same, right? So um, if I have over here xi is si plus ui, then apparently xi dot is going to be si dot plus ui dot. So ui dot, the way in which the difference moves, right? The way in which the difference evolves is going to be this xi dot minus, well, this s dot, because the ith component, all the components of s are of course the same. And we already know how S evolves, right? Because S is just, right? S is just a coordinate on the fully synchronous manifold. So we know that Si dot is just going to be F of S, right? Per definition, because we are on the fully synchronous manifold, because I said that big S is one tensor small s, and on that manifold, you can, of course, also just plug that in and verify that by direct calculation. But on that manifold, this fully synchronous manifold, the dynamics of the only coordinate describing it, the S is, of course, S dot, is F of S. So that is fine. So then we only have to focus on this xi dot. So that's just a matter of plugging in. So this is going to be, I have that F of xi, but xi is just, of course, equal to s plus ui, right? Just as we have before. Now I'm also going to copy this over here for s dot. So I'm already going to say f of s. And now, of course, I have to contend with the whole coupling term that I have over here. But I claim that this is quite easy. I claim that if I plug in xj minus 2 xi plus xk, that this is just going to be uj minus 2, so everything the same, minus 2 ui minus, or plus in this case, uk. And why is that? Why is this exactly the same as xj minus 2 xi plus xk, right? Is why can I just replace the x's by the u's? Because the difference between xi and ui is just an s, which does not depend on the index I. So what I'm subtracting is just s minus 2s plus s, which is 0. So that's what I'm going to use here. So here I will have plus the alpha, and then we have that whole sum, which I will just abbreviate, right? Because we know the sum is over j and k, because I is the index that we fix. And then here we will just have h of that difference of the u's. So that was uj minus 2 ui, and then we have a plus uk, right? Just using that the s part vanishes on that on this difference, which is of course precisely corresponding to the fact that x1 is x2 is x3 and so forth was flow invariant, and that on it we have precisely these dynamics, right? I'm really saying the same thing in different calculations. So all right, so we're in good shape. Why is that? Well, recall that h of 0, no, I didn't say that. H of 0 is equal to 0. That was our assumption. H is not necessarily linear, like we said, but it's 0 and 0. Also, I can do Taylor expansion on H, and I can also do Taylor expansion on F, and F does not necessarily vanish in 0. However, we see S as some value and U as some small perturbation. So then here we can assume we can apply Taylor's. So approximately what we get is df at the point S, or rather in the curve S, right? Because we will again get a linear time-dependent ODE times UI. And then what do we get over here? Well, we can just replace H by D of H, right? D of H at 0. So we get plus alpha. And so D of H is a linear map. So I can just take that out over here. The derivative at 0, right? Because the u's are all small perturbations. And what we plug in here is that entire factor, which is that entire sum, right? So this A I J K, right? Because D of H at 0 is linear. So I can just take that in once I replace H by its linear approximation. So here I just get those bunch of U's again, right? Exactly the same expression as I have on top, that uj minus 2 ui plus uk, right? So just this expression. Now, this is all very handy because remember, we have a definition of L over here, which is precisely what we had, which is precisely what we found, right? So this L is essentially appearing precisely here. And note that this is just a sum of factors in Rk. And then we have d of h0 applied to that sum or difference, sum and difference of factors. So if we take all that together, I can just say, say that ui dot is approximately, right? But we have ways of making that precise, that this is approximately equal to df of s applied to ui, right? And then we have the minus, because remember we defined that that L, that Laplacian, with a minus because we wanted to have a plus 2 at the diagonal, or plus 4 or whatever. Instead of a minus, we gave it a 0. And then here we just have L of u ith component, right? And that is just exactly plugging in what we had, what our definition was for L, right? This expression is precisely Lx, or if you want, Lu, the ith component. So finally, what we can do is we can stack all the u's together, right? So we take one big factor which lives in Rk, in R, I should say in R n times n minus 1 times k, right? Or if you want, it's a subset of Rn times k. We're just stacking them all together. And then this was approximately equal to the identity tensor, this linear map over here, d of s. And then minus alpha, and here we have that L tensor, that dh at 0. Right? This is precisely how the Kronecker product works. This is precisely how the tensor product works. All right, so far so good. So all of that applied to U, right? Which is this big factor, which is all those components from RK stacked together. I hope I have enough brackets. I think I do not. And so now we have a single, again, linear but time-dependent ODE for U, for the vector U. But we can do better. We can actually split this into its components, right? Because remember that I said that U is this sum from L is 2 to N VL tensor YL, where the VL were just fixed eigenvectors of L, but the YL are of course the variables. So if we plug that in, then we of course just see here that the sum of that VL again does not depend on time, but the Y's they will. So I just get YL dot. This is or is approximately, but at this point I will just write is equal to. And so now for V, we get to write that whole sum, right? So we get to write that sum of the VLs tensor these YLs. And then just by the rules of tensor notation, we precisely get to see what it does for each of these terms. So you just have to apply, right? You just have to apply the first one to the first and the second to the second. And of course, by the way that we set things up, this exactly goes well because this VI behaves very well with respect to the identity. Every vector behaves well with respect to the identity. But the VI also behaves very well with respect to the L because remember, the VIs are precisely the eigenvectors for the corresponding eigenvalues. So if we put all that together, we just get, well, a sum here, VL tensor that DFS. So we can't really get from under there. We can't really do anything about that. So we just get DFS times that Y. Right? That's just the second component. And then we get minus alpha. And now we use that VL is an eigenvector of L. So we get that lambda L. And again, a VL tensor. Well, that dh of 0 still acts on that YL. So now we just get here dh of 0 times YL. So this is very nice, right? So we can just freely shove around that dh of 0 because this is just a linear map. The derivative is a linear map. And this is, of course, because we were doing right? We're doing first order approximation because recall h itself is not linear, but this turns out to be not a problem at all. So what I can now do is I can take these two numbers, which are just scalars. This is supposed to be an L, and put them in front. So what I then get is just that the first component of each of them is just VL. So I can write everything as VL. The sum is, of course, over L. L is 2 to n, right? Because V1 was 1, which was the other eigenvector, but V2 is the eigenvector corresponding to lambda 2, and so forth. So the sum is, of course, from L is 2 to n. And then here I just get df of s, and then I get minus that alpha lambda L that I put in front, right? dh of 0. And then here, just everything applied to that YL. So now you can give a very rigorous argument why you can completely forget about the sums and you can completely forget about these VLs. The rigorous argument is using some dual basis to the V1 to Vn and applying that to these vectors and noticing that the only thing that remains is the right component. But another way to see that is that the VLs, they are already linearly independent. So the tensor products are also linearly independent. So if we have this identity holding, then the only way that is possible is if it holds for every component L. And this is in fact equivalent. So what we get is simply that YL dot, right, which is just this component over here, will have to be equal to this component over here. So then finally we end up with YL dot is df of s minus alpha y of L, right, minus, and then we had that derivative of h, which was our best approximation, our linear approximation of h, of course, at 0. And then we have that YL. So finally, what we have done, as precisely in the case with dyadic networks, right? Because these were hypernetworks, but as exactly in the case with dyadic networks, under the assumption that our Laplacian is a symmetric matrix, we have pried out precisely L, or precisely n minus 1 linear but time-dependent equations for the y's. And again, so we can call this ut, or rather ul of t. So again, we find that if all of these equations, so all of these n minus 1 equations have that 0 is stable in some appropriate sense of stable, of course. So if I go a little bit away from 0, it goes back to it, then I will be able to conclude that this part over here vanishes, and therefore we have synchronization. Again, of course, I have to be a little bit precise. I have to find some notion of stability for this linear system, which was just an approximation of the real system, right? Because we threw away a lot of Taylor coefficients, right? This is only an approximation. So we have to make sure that we get some notion of a robust sense of stability, in the sense that if we slightly change that ULT, that it it remains stable. It remains to have our notion of stability. And then indeed we can conclude um, exactly in the same way as in the lecture notes that for the big nonlinear system that we started with, this one over here, we indeed have that the synchronization manifold is stable. So we've reduced it to exactly the same situation as we had for networks. So it turns out that for hypernetworks, nothing really changes, except of course at the level of the linear algebra, right? Because the only thing that remains is to study the spectrum of this new Laplacian, right? So this new Laplacian is in some sense different from the Laplacian that we had before, right? Because we started with a network, and with the network we only have minus ones at the minus ones and zeros at the off diagonal, and then we just have the degree on the diagonal. But what we can have here is we can of course have something like we can have like a minus 2 here. So in some sense, we can see this as again a Laplacian for a graph, because matrices, they are not so fine-tuned that they see the difference between networks and hypernetworks. But so in some sense, we can see this as the network for a single the Laplacian for a single network, but now with weighted connections, right? So there could be a connection with weight 2, or if you want, this can be seen as two edges taking place between exactly the same two nodes. But nevertheless, what you can do is you can start analyzing the spectrum using much the same techniques that you use for networks. And then you can actually start concluding rates of synchronization, for instance, based on this lambda 2, right? Based on this Fiedler value. So one thing that's kind of interesting about this point of view is that you can also see this Laplacian over here as the sum of two Laplacians corresponding to more to things that are more honestly networks. So how do you do that? So let me quickly sketch that. Well, let me first do it here. Suppose this h over here was just linear. So we know it's not, but we could have assumed from the start that it's linear, or we know that from the equations that we pry out, we only care about the linear part of h. So it's not a stretch to assume from the get-go that h was already linear. So if h is linear, then what I can do is I can take this whole term over here, and I can simply write it as h of x j minus xi plus, of course, plus h of xk minus minus xj. And this is something that people very often do in when studying hypernetworks, because really one of the main questions, this is supposed to be an x, one of the main questions that you get in the world of hypernetworks is, to what degree are hypernetworks different from just networks? Because if I take this entire term over here and I just replace it by this, then what I see is that I just get just two networks overlaid with each other. Of course, we have to contend with those sums, but if we take all of that together, then what I see about this LXI, right, so this is just the ith component of that of this guy over here. This is just going to be, if I split this exactly in the same way as I did up there, then this is just going to be the sum of, say, the k's, right? K is 1 to n, of, well, I don't really care about the L's, or these are the J's anymore. So I can just put here the sum of J of A, I, J, K, right? And I just put that together, and let's call this this entry over here B I B I K, because it does not depend on J anymore because we've summed over all the J's. And then here I just get indeed X K minus Xi. So this is going to be my first component. And you see that this is just diffusive coupling with a normal network whose adjacency matrix is given by this BIK. And of course, I also have to get that second part. So now I get the sum over the J's. And I'm just going to split off the sum over K this time, right? Because I don't really care that much about it. And now I'm going to get just, let's see, the sum over Aijk again, of course. But now, so the sum is over K's, which means that what I get over here is going to be just a regular two tensor, just a regular matrix again. I can call this, for instance, CJK. Right? And then here I just get xj minus xi. So I hope you agree with that trick. I've just done exactly the same as I did up top. I've just taken that term. Let's see. Yes, I've just taken that term xj. Sorry, this is of course an I, right? I've just taken that that term minus xj minus xk plus 2xi, and I've just split them as this term and this term. Oh, I see that I've, of course, given it a minus sign because the xi I wanted to have positive. But that's all that there is to this. So now all of a sudden I have two new adjacency matrices, and correspondingly I have two new Laplacians. Right? So let's call that L1 and let's call this one L2. And if I then change the indices, then I see that I've simply written this L as the sum of two others. And so now you can start playing with the eigenvalues of L1 and L2 and see how they compare to the eigenvalues of L. And then you get into some pretty interesting territory. Namely, what you find is that the Laplacian, the Fiedler value of this L has to be strictly, or well, not necessarily strictly, but very easily strictly, but it has to be bigger or equal to the Fiedler eigenvalue of this one and the Fiedler eigenvalue of that one. So in other words, the Fiedler, so it will be bigger than the maximum of that of these two, which means that synchronization will go at least as good as any of these individual networks that you pried out. And that is a result that's called a Fiedler monotonicity, um, which I will not prove here, but it essentially tells you that hypernetworks have better synchronization than either of their components. So I'm going to stop with that. We can explore that a little bit better in the lectures, but that is something that's ongoing research in some sense. This is something that people see over and over again. Synchronization under certain conditions seems to be, and again, you need to have the right measure. What are you comparing? But seems to be easier for hypernetworks than for networks in a very rough nutshell, of course. So that is the end of this bit about hypernetwork systems. So really what we've done at this course is we first focused completely on developing machinery for networks, and then we've shown that this machinery actually goes through in the situation of hypernetwork coupled systems. And we have found some interesting relations between the rate of synchronization for this hypernetwork and the two networks that you can essentially um, um, decompose it into, right? Because that's of course what you're doing. You're just seeing a hypernetwork and you're pretending like there is only the links and not the whole triangle, if you will. Of course, like I said, there are many other interpretations of this. This is ongoing research, but that hopefully gives you a flavor of some of the things that you can do with hypernetworks that you could also do with networks. So with that, I would like to end this lecture. I hope this was convenient to you. Again, if this went a little bit too fast, I would first recommend reading the lecture notes because I'm only using techniques here that are in those lecture notes. So that was it. Thanks.